In this section, we are going to see the analysis of bridge full wave rectifier. The first parameter is DC output current indicated by IDC. Everyone know that the DC output current is average value of output current, which is given by 2Im divided by pi. The center tapped full wave rectifier has also the same value of DC output current. And the next parameter is RMS output current IRMS, which is equal to Im divided by root 2. And the third parameter is ripple factor, which is the measure of AC component present in the output waveform, and ripple factor is equal to 0.483. The center tapped full wave rectifier has also the same value. And the fourth one is efficiency. Eta is equal to 81 into RL divided by 2RF plus RL. When you compare with the expression of efficiency for a center tapped full wave rectifier, that expression is 81 into RL divided by RF plus RL. But in the case of a bridge full wave rectifier, in the denominator the two RF terms comes, whereas in center tapped full wave rectifier, here there are only RF terms. Here the two RF is because of the presence of two RF is because of here at a time in bridge rectifier, at a time the two diodes are conducting. When omega from 0 to pi D1 and D3 are conducting, and omega t from pi to 2 pi D2 and D4 are conducting. That means at a period of time or at a interval of time that there are two diodes are conducting. That is why each diode having an internal resistance of RF. So at a time period or an interval of time period, there are two diodes are conducting. So effectively the resistance offered by these two diodes is 2R. That is why in the expression of efficiency the 2R terms comes. And the fifth parameter is peak inverse voltage, and is given by Vm, whereas in a center tapped full wave rectifier the peak inverse voltage is 2 Vm. So remember, in bridge rectifier peak inverse voltage is Vm. And the next parameter is form factor, which is equal to 1.11, and the peak factor is equal to root 2. And the next parameter is frequency of output, which is same as that of center tapped full wave rectifier. The output frequency is equal to 2 times frequency of supply. And the next parameter is transformer utilization factor, which is equal to 0.81 into RL divided by 2RF plus RL. And next is what are the advantages of bridge rectifier over center tapped rectifier. In a bridge rectifier, it has smaller PIV, which is equal to Vm, whereas in center tapped rectifier peak inverse voltage is 2 Vm. And the next point is does not require center tapped transformer. Bridge rectifier we are using a normal step down transformer. And the next point is greater transformer utilization factor. In bridge rectifier transformer utilization factor is 0.81, whereas in center tapped full wave rectifier it is 0.69. And the next point is the bridge rectifier can be used as a high voltage rectifier. When the bridge rectifier is used as a high voltage rectifier, diodes should have higher breakdown voltage. For example, a diode with a breakdown voltage of 310 volt. So one of the application of bridge rectifier is it can be used as a high voltage rectifier. When we are using the bridge rectifier as a high voltage rectifier, the diode should have a higher breakdown voltage because we are applying a higher voltage to the diode. So to withstand the diode should have higher breakdown voltage capability. Next we are going to discuss a problem. First I am reading the question. A bridge rectifier is applied with a 240 volt AC supply, 50 Hz frequency. If RL equal to 10 kilo ohm, calculate following values. First we have to determine DC output current and voltage and RMS output current and voltage, peak inverse voltage and frequency of the output voltage. So first we have to write the given values. So the first value given is a bridge rectifier is applied with a 240 volt AC voltage. So I can write this value is VRMS. The 240 volt is VRMS value. Okay, remember that the AC quantities, whether it is AC voltage or current, it is expressed in terms of its RMS value. Root means square value. So a bridge rectifier is applied with a 240 volt AC means it is the 240 volt is an RMS value. Root means square value. So VRMS, the applied input voltage, has an RMS value of 240 volt and the frequency of the supply is 50 Hz. The unit of the frequency is Hz and the unit of voltage is volts indicated in V. And also given that the load resistor RL is equal to 10 kilo. RL is equal to 10 kilo. And here in bridge rectifier we are using total of 4 diodes, and the question they are nothing specified about whether these diodes are ideal or not. So nothing it is given, so we can assume that the diodes are ideal. So the forward resistance, diodes forward resistance, or the resistance offered by the diode when it is in forward bias mode, RF, so we can take it is a 0 ohm. The unit of resistor is ohm. Okay, so these are the given values. So first we have to find out DC output current and voltage. So given that VRMS is equal to 240 volt, so what is the expression of VRMS in terms of Pm? VRMS is equal to all the expressions. I have explained all the expressions in the previous classes. So VRMS is equal to Vm by root 2. So I can write Vm. Vm means the maximum value of the input voltage. Vm is equal to VRMS multiplied by root 2. So I can write Vm is equal to, VRMS is given, it is 240. So Vm is equal to 240 root 2. Vm is equal to 240 root 2 volts. Okay, the question is to find out DC output current and voltage. The DC output current indicated by IDC. DC output current indicated by IDC is equal to 2Im divided by pi. So to find out the DC output current, first we have to find out the maximum value of current, Im. So the maximum value of current Im is equal to Vm divided by Rf plus Rl. Consider, all of you know that what is Ohm's law. Ohm's law means V is proportional to I, and the result we can write the I is equal to V by R. Actually here also we are applying Ohm's law. We have to find out the maximum output current. So which is equal to maximum output voltage divided by the resistance offered by that path. Then recollecting the working of bridge full wave rectifier. When omega t from 0 to pi, there are two diodes are conducting, and so that the current is flowing through these two diodes and the load resistor also. So the total resistance offered by that path is 2Rf plus Rl. So I can write the maximum output current Im is equal to maximum voltage divided by 2Rf plus Rl. Then here we are assuming that diodes are ideal. That means Rf equal to 0. So I can write Im is equal to Vm divided by Rl, which is equal to, we have already found out the value of Vm. Vm is 240 into root 2 divided by RL value, load resistor. It is given that value, which is 10 kilo ohm. Okay, 10 kilo ohm, we can write it as 10 kilo ohm means 10 into 10 raised to 3 ohm. 1 kilo ohm is 10 raised to 3 ohm. So 10 into 10 raised to 3. Then do this calculation. We will get 24 root 2 into 10 raised to minus 3 amperes. The unit of current is ampere, indicated by A. So this I can write 24 root 2 milliamps. Milliampere, 1 milliamps means 10 raised to minus 3 ampere. So Im, the value of Im is 24 root 2. So we can find out the DC output current IDC. IDC is equal to 2Im divided by pi, which is equal to 2 into Im value is 24 root 2 divided by pi. So this becomes 48 root 2 pi milliamps. Remember, the maximum value of current Im is expressed in terms of milliampere. So the IDC also milliampere. So the answer is 48 root 2 divided by pi milliamps. Next we have to find out DC output voltage. DC output voltage indicated by VDC, which is equal to, VDC is equal to 2 Vm divided by pi. Also we can use, already we know that value of IDC. So the DC output voltage means the DC output voltage, DC voltage developed across the load resistor RL, we know that what is the DC value of current flowing through the load resistor, which is IDC. So I can write VDC is equal to IDC into RL. Both expressions are valid. So we know that value of IDC is 48 root 2 divided by pi, and the RL value is 10 kilo. That is 10 into 10 raised to 3. And also IDC is in milliamps, so we have to convert it in ampere. So 1 milliampere is 10 raised to minus 3 ampere. So here 10 raised to minus 3 terms also come. So this is equal to 480 root 2 divided by pi volt. Next we have to find out, and the B part, I will go to the question. The B part, next we have to find out the RMS output current and voltage. So the RMS output current indicated by IRMS, which is equal to, we know the expression IRMS equal to Im divided by root 2. So which is equal to, Im value is 24 root 2 milliampere divided by root 2. So the answer is 24 milliampere. The value of RMS output current is 24 milliampere. And next we have to find out the RMS output voltage. RMS output voltage indicated by Vrms, which is equal to Vm divided by root 2, which is same as IRMS into load resistor RL. So which is given by IRMS value is 24 milliampere and the value of RL is 10 kilo ohm. 10 raised to 3 and 10 raised to minus 3. This will becomes cancelled. So I can write Vrms equal to 240 volts. And the third question is, what is the peak inverse voltage? The peak inverse voltage PIV is equal to Vm. Already we have found out the value of Vm, which is equal to 240 root 2 volt. And the last question is, what is the frequency of output voltage? The frequency of the output voltage is output voltage or current, both are same. Output voltage is equal to 2 times frequency of supply frequency of the supply voltage. So the supply frequency is given as 50 Hz. So 2 into 50, which is equal to 100 Hz. And the second question is, an AC supply of 230 volt is applied to a half-wave rectifier circuit. The half-wave rectifier circuit is shown, and through a transformer of turn ratio 10:1. Find the output DC voltage and peak inverse voltage. So here I am showing a circuit diagram of half-wave rectifier and assuming diode is ideal one, and the turn ratio of a transformer is 10:1, or turn ratio is 10:1. That means the number of windings in the primary and the secondary are in the ratio of 10:1. So I can write primary to secondary turns ratio is n1 by n2 is equal to 10 by 1, which is 10, where n1 is the number of turns in the primary winding and n2 is the number of turns in the secondary winding. And also we know that the basic expression of a transformer, we can write n1 by n2 is equal to n1 by n2 is equal to v1 by v2, which is equal to I2 by I1. Okay, so n1 is the number of turns in the primary winding, n2 is the number of windings, number of turns in the secondary winding, and v1 is RMS value of voltage at the primary winding and the V2 is RMS value of voltage at the secondary winding. Similarly, what is I1? I1 is the RMS value of current at the primary winding, and I2 is the RMS value of current at the secondary winding. Again goes back to the question. In the question it is stated that an AC supply of 230 volt. I am already stated that here 230 volt is an RMS value, okay, which is applied to a half-wave rectifier. That means in this diagram, this is 230 volt RMS value. Okay, so I can write V1 is equal to 230 volt. So substitute these values into equations. N1 by N2 is equal to V1 by V2. That is V2 is equal to N2 by N1 into V1, which is equal to N2 by N1 is 1 by 10 and the V1 is 230 volt. So 230 into 1 by 10, which is equal to 23 volt. This 23 volt is the RMS value of voltage at the secondary winding. So we got RMS value of voltage at the secondary winding is 23 volt. So Next we have to find out the value of Vm. Vm is equal to Vrms into root 2. Vrms into root 2. Here the Vrms means the value of RMS value of voltage at the secondary winding, which is given as V2. V2 is 23 volt. So 23 into root 2. So 23 root 2 volt is the maximum value of voltage Vm. Okay, so in the question we have to find out the output DC voltage. The output DC voltage is VDC. Output DC voltage VDC. VDC is equal to IDC into RL. The IDC is the output DC current, which is equal to IDC is equal to, this one is a half wave rectifier, so the IDC equal to Im divided by pi. Substitute value of IDC into VDC equation. So I can write VDC is equal to Im by pi into R, where Im into RL is Vm. We know that value of Vm, which is 23 into root 2 divided by pi. So this is the value of VDC, DC output voltage. Someone have one doubt about that. Consider this equation. Vrms equal to Vm equal to Vrms into root 2. But while I am talking for the working of a half wave rectifier, there I am written Im is equal to 2 into Irms, or Irms is equal to Im by 2. But here I am using Vm is equal to Vrms into root 2, because goes back to the circuit diagram. Here the voltage at the primary and as well as secondary is a sinusoidal waveform. That is why I am taking the Vrms is equal to Vm divided by root 2. This expression Im is equal to 2 RMS, or Irms equal to Im by 2. This is the expression of, or this is the expression related to output of a half wave rectifier. That means like this. The waveform of the RMS value of the output of half wave rectifier is Irms equal to Im by 2. But in the case, the voltage at the primary and the secondary are sinusoidal form, like that. Sinusoidal form. For a sinusoidal waveform, Vrms is equal to Vm by root 2. Okay, hope that all of you got the concept. Okay, so we got the output DC voltage is equal to 23 root 2 pi. And the next question is, find out the peak inverse voltage. The peak inverse voltage PIV. What do you mean by PIV? During the negative half cycle of the AC supply, the diode is reverse bias and hence conducts no current. Therefore, the maximum the secondary voltage appears across the diode, and this maximum voltage is termed as peak inverse voltage. The PIV is equal to Vm. Vm value is 23 root 2. So PIV is 23 root 2 volt. And the third question is, the applied input AC power to a half-wave rectifier is 100 watts. The DC output power obtained is 25 percentage, not 25 percentage. This one is 25 watts. Okay, 25 watts. Determine rectification efficiency. So we know that expression of rectification efficiency, or simply we can say efficiency. Rectification efficiency indicated by eta. Eta is equal to, what is the expression? The DC output power divided by input power. That means input power is in the form of AC. So AC input power. So in the question it is stated that the DC output power obtained is 25 watts. The unit of power is watts and the unit of energy is joules. The power has one more unit, joule per second. So watt is the unit of power and also joules per second. Joules per second is also unit of power. So the DC output power is 25 watts and the applied AC input power is 100 watts. So efficiency is 100. So this I can write this is 25 percentage. So the rectification efficiency eta is 25 percentage. What is the maximum efficiency of a half-wave rectifier? It is 40.5. 40.5 percentage is the maximum efficiency attained by the half-wave rectifier. And the next question is, a half-wave rectifier is used to supply 50 volt DC to a resistive load of 800 ohm. The diode has a resistance of 25 ohm. Calculate RMS value of input voltage required. So the output DC voltage VDC is given as 50 volt. Okay, that means the half-wave rectifier is used to supply, the rectifier must be supply an output voltage of 50 volt. So that is why VDC I am taken, the output voltage VDC is equal to 50 volt, and also given the diode resistance RF. Diode forward resistance RF is given 25 ohm, and the load resistor RL is given as 800 ohm. Question is to find out RMS value of input voltage required. So here I am writing, let Vm. We have to find out the value of Vm. Vm be the maximum value of AC voltage required. Okay, Vm be the maximum value of AC voltage required. We have to find out what is the value of Vm. So for that we know that the expression of VDC, DC output voltage, VDC I can write, which is equal to IDC, the DC output current into the load resistor RL. So we know that VDC in terms of IM. VDC, we know that IDC in terms of IM. IDC is equal to the DC output current is equal to IM divided by pi. So this is VDC is equal to IM divided by pi into load resistor RL. Then what is the value of IM? The maximum value of output current. IM is equal to maximum value of output voltage or maximum value of voltage applied. Vm is equal to Rf plus RL. Or in the case of a bridge rectifier, what is the expression for IM? That also Vm divided by 2Rf plus RL, because there in bridge rectifier 2 diodes are conducting simultaneously. So there comes 2Rf. Here only one diode since it is a half wave rectifier. So IM is equal to Vm divided by Rf plus RL and also pi also into RL. So, and VDC is given value, VDC is 50, 50 is equal to Vm we have to find out, and the pi RF value is 25 ohm and the RL value is 800 into 800. So I can write Vm is equal to 50 into pi into 825 divided by 800. Vm is equal to 50 into pi into 825 divided by 800. So the cancelling the common terms, we will get Vm is equal to 162 volt. So a maximum AC voltage of AC voltage of 162 volt. 162 volt is required.